Hey, hey, hey guys, let's talk about free energy and equilibrium. Yes, let's talk about free energy and equilibrium. I love to talk about free energy and equilibrium all day long. You know, I'm kidding. Oh, look at these beautiful colors I have to choose from. I gotta share my screen. Zoom, free energy and equilibrium. We're getting close to the end. It's kind of sad. I'm so sad. Seriously, I'm gonna miss you guys. This has been quite a process. I'm kind of sad that I'm getting to the end. However, I have a whole nother class to finish, so I don't need to be sad. Free energy and equilibrium. Okay, that's ugly. I'm not keeping that. What are we gonna say? Sorry, guys. Sorry. Free energy and equilibrium. How do we want to start that? Let's see. So what do we know? We know that what we're going to relate here, guys, is delta G and K. And it's just logic, right? Remember, if K is greater than 1, right, then EQ lies to the right? It is product favored, and it proceeds in the forward direction. The process does, right? Readily, right? It readily proceeds in the forward direction. Well, what does that mean in terms of delta G? Well, that means delta G is negative, 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 right? Very spontaneous. Very negative. So you can get some very, very negative values for delta G, okay? And when you do, it means we're very spontaneous, and that should relate to very large values for K. I mean, some really large exponents here, okay, or small. If we have the positive delta G and a great magnitude, meaning a very, very positive, right? The magnitude doesn't have to do with the charge. It means the size of the number. So a very large magnitude delta G, whether negative or positive, let's say it's very positive. It means it's very non-spontaneous, right? That means equilibrium would lie to the left, right? Does not proceed in forward direction. So we can relate being spontaneous to the equilibrium position, right? Does proceed in forward direction if we have the negative spontaneity. Delta gives free energy. Okay, and that should make sense. So if we have a very positive delta G, we would see K's being much less than 1, right? EQ lies to the left. We are reactant favored, and this reaction does not proceed in the forward direction, okay? So we've related delta G and K. One thing I would like for you to be aware of is this equation, delta G equals negative RT ln K. It could be standard or not, all right? This is obviously your Gibbs free energy. It's in kilojoules per mole, all right? This is your gas constant. Look at the units, kilojoules here. we're going to need to get that in our gas constant. So this gas constant must be 8.314 joules per mole Kelvin, or 0.0081314 kilojoules per mole Kelvin. I think you need to think about this in terms of the units, right? It will be provided to you in joules, but you will be using it in a kilojoule form. Your T is your Kelvin temp, right? Obviously, I should be using a different color right now. And K, guys, is your equilibrium constant. So I was taught to remember this equation by saying rat link, okay? Because it's R, T, L, N, K. That's how that's how I've memorized that equation. Another thing before we finish up here and say goodbye is that at equilibrium, delta G is equal to 0. Okay? You need to be aware, you've got to be aware that at delta G at equilibrium, our Gibbs free energy is 0. We are at maximum stability for a system. There's no work to be done. Nothing else can be done. It is the battery is dead. It can't do any more work. It's done. Okay? So you also need to realize that phase changes are also at equilibrium. Okay? Therefore, when we do delta G equals delta H minus T delta S for a phase change process, or system at equilibrium, right? Or system at EQ, we can do this. Set equal to 0 because we are at equilibrium. We're left with 0 equals delta H minus T, minus T delta S. And if we rearrange that, we have delta H equals T delta S. All right. Now, this temperature can be solved for. This temp is the phase change. If this process is a phase change temp, right? Because we said at equilibrium, phase changes are at equilibrium. And at that point, delta G is equal to 0. So we end up with this equation down here. And this temperature is the temperature at which this phase change will occur, right? Remember, phase changes are temperature dependent. And if we have an endothermic and a positive entropy, gaining entropy, it would be that temperature and above, right? Temp and above, that would be if like boiling or melting, right? Because we need high temperatures for those because that's a positive delta H and a positive delta S. And it is that temp and below if, let's see, condensing or freezing, right? Because that is the negative delta H and the negative delta S. So we need cold temps, right? Cold temps here required for these processes and hot temps here. So we need to be able to specify, is it the temp and above or is it the temp and below? But if asked, what temperature will this occur? You need to solve for delta T. I mean, you need to set your delta G equal to 0 and solve for T. Good stuff. Good stuff. I'm sad. I'm almost finished.